In our bodies, a cell from your foot and a cell from the brain share the same genome. It is clear, however, that a foot and a brain are very different. Scientists have long wondered how cells choose which genes to turn on and which to turn off. To understand this, scientists have looked at bacteria. Bacteria are very old compared to humans, and over time have created clever ways to do this. One example is by cellular communication, or quorum sensing.
Quarom sensing, or cell phones, is the way cells communicate. All cells in your body need to work together in what's basically a huge group project. Imagine a group project with thousands and thousands of members working on something as complex as our bodies. That takes a lot of organization. As I'm sure you've heard before, teamwork is one of the most important ways things use to get the job done. We know how humans use teamwork, and this is how cells use teamwork. Here's a little bit of vocabulary to help you understand quorum sensing.
Some cellular processes require cooperation from neighboring cells to be effective. One example is bioluminescence, or the ability of cells to glow. Another is virulence factors. These are the weapons that bacteria use to infect and harm others. Neither of these processes are effective if performed by only one cell. Bacteria must be able to communicate and coordinate with others around them.
Communication is key.
This task is quite easy for humans, but presents more of a challenge for bacterial cells. Quorum sensing allow bacteria to sense how many other cells are around them. Bacteria are constantly making a small molecule called an autoinducer. This molecule is able to pass in and out of the bacteria that made it and also others in its environment. As the bacteria divide and increase in number, the concentration of these small molecules will also increase. Once this concentration reaches a certain threshold, these small molecules are able to activate transcription factors. Transcription factors are proteins which will go turn target genes on or off. This allows bacteria to express certain genes only in the presence of many other bacteria.
This is also the reason our bodies know not to put a foot where our head goes and a head where our foot goes. Using this, bacteria can sense who's around them in their environment. They can decide if they're around friends or foes, and if they should work with them or prepare to defend themselves. One example of friendly bacteria communicating with one another is the squid light organ. They sense others around them and help the squid to glow at night or bioluminesce. The squid likes having the bacteria in there because it helps them glow at night and survive. The bacteria like to live in there because they get to eat and have a home, so they can also survive. During the day, the squid likes to rest. But at night, the squid likes to hunt. And how can it see at night if it's too dark? It uses the bioluminescence. How exactly does this bioluminescence work using quorum sensing? One bacteria is so tiny it won't make a difference if it glows alone in a big ocean. It needs to work with friends. During the day, the squid releases 95% of this light-causing bacteria. While it sleeps, the bacteria grow and multiply, so at night, when it's ready to hunt, it has plenty of bacteria that glow.
Bacterial quorum sensing can be helpful to organisms like the squid, but it also plays a dangerous role in infectious disease.
Our immune system patrols our bodies looking for bad bacteria. When a bacteria tries to hurt us by itself, our immune system could easily stop it. Some bacteria use quorum sensing to work together to form a sneak attack on our immune system, which is much more effective at making us sick. This happens because the bad bacteria hide and our immune system is suddenly outnumbered. Now, scientists are using their knowledge of quorum sensing to develop drugs to prevent this bad bacteria from communicating, which would prevent these sneak attacks. Then, our immune system could have a much better chance of fighting the disease. Just like a group project where members can't talk to each other, absolutely nothing would get done. If a cell could talk to you, he'd say, "Thanks for learning about quorum sensing."